And I'll review a little bit. I'm going to do a little bit of reviewing here. One of the classes, I don't think one of the classes didn't get to look at a submarine. Is that you guys? Did we look at the a submarine? I think that was you. Is that Matt? Do you remember talking about a submarine at all? Okay, let's take a look. Look at your handout sheets. And I looked last night. I was actually watching for almost 30 minutes. I was looking at different videos, and there just weren't very many YouTube videos that were that good. I saw one where it was like 1950s or 60s. If you were in the Navy, they had made you watch these films, these black and white films, and they were trying to teach you a little bit of science, you know. And so if you were in the Navy and you're going to be on a submarine, they wanted you to watch a little video, and that's the way they made all their science videos back then. It's kind of classic. But I just didn't think it was worth our time, so I'm just going to go ahead and show you the handout sheet I have here. I know it's Monday, and I don't know what happened this weekend. Maybe you forgot about school at all. I don't know what happened. But let's see if we can get back into the swing a little bit here. As far as the submarine, here's the like a cross section of the submarine. And so the people are in here, and this is the inner hull. The inner hull is really made strong, and that's what really protects them from being crushed. And then they have the outer hull, and then in between these two hulls, there are ballast tanks along the side of the submarine. So let me ask you this question. On a Monday morning, if you can answer this question on a Monday morning, you probably understand this concept pretty well. Right now, which one is greater? Look at the submarine right here. It's docked at the harbor, and people are getting in the submarine. And which one is greater there, weight or buoyant force? Okay, take a look right there. They're getting in the submarine, and which one is greater, weight or buoyant force? All right, what do you think? Say what?
Buoyant force.
How many people think buoyant force on a Monday morning? What?
I think it's equal.
What?
I think it's equal.
You can change your mind.
Yes.
How many people think it's equal? And it is. It has to be equal because it's floating, right? And it's floating, so they have to be equal. But how do you get a submarine to how does it go down? I need the weight of the submarine to be bigger than the buoyant force. So what they have is these things called ballast tanks, and you can read this, but all they have to do is open up a door. Actually, they can open up here. If they open up these doors down here and then let the air out like this, then the water will flood the ballast tanks. So if you flood the ballast tanks, water has a density about 1,000 times greater than air. So you just increase that space. What was in that space, you increase that space weight by 1,000 times. Now, that'll make the weight of the submarine greater than the buoyant force, and it'll go down. I don't want to get too sophisticated here, but there are main ballast tanks, and then there are ballast tanks in the front and the back, and that can help them if they want to go down like this. What if they want to go down, if this won't go down like that, you can just flood the main ballast tanks. They have these other ones that, what if you flood this one? See, they didn't go and point downwards like that. Those are called trim ballast tanks. So let's say you're down at the bottom now, and let's say at the bottom, and you say, well, now we need to go up. Now we need to go up. How do we do that? How does a submarine go up? What now? Yeah, I got to get rid of that water. But how do I do that? How am I going to get rid of that water? I'm sorry, go ahead.
Did you put your attendance out and I missed it? Or did we?
No.
Okay, can you just tell me and I'll write it down?
No. It's none. No need.
Zero.
None, yeah.
That's easy to write.
None.
Thank you.
I'm sorry. Darn it. What was I saying? Oh, submarines? Yeah, so how do you get up? You're at the bottom of the ocean. How are you going to get up?
Oh,
And, you know, what do you think? Any ideas? Yes.
Expel water.
What?
Expel water.
How?
Bilge pumps.
Wait now. A bilge pump on a regular ship simply takes the water and throws the water outside the ship. That won't work here because, see, when I take if it's flooding my ship, I can take it out, and there's still going to be air there and everything. But here, I can't take the water out without leaving a vacuum, right? Go ahead, Nathan.
They use compressed air to force the
That's right. There's a huge amount of compressed air tanks in there, and so they're on the surface. They push the pumps, they push air in there, they compress a lot of tanks, and so then they, instead of flooding the ballast tanks, they blow the ballast tanks. So what they would do is take compressed air and say, push that water out, and then the submarine buoyant force will be less than the weight. So buoyant force will be greater than the weight, and the submarine will come up. Now, if you want to study that, there are all kinds of things the submarine has. They even have little wings on the side. You can actually come up and you can go like this. You can do that. Of course, they all have motors. They have engines. And if you really get into modern submarines, the modern submarine is meant to stay underwater and not be found. The modern submarine that we have and other countries have, they're nuclear submarines. They are not meant to be noticed. Their job is to go around the world and not have people know where they're at. The theory is that if you were to launch a nuclear attack on our country and you don't know where our submarines are, the submarine has plenty of nuclear warheads that essentially you would have. If you try to annihilate our country, your country would be annihilated. And that's the job of the nuclear submarine. So with nuclear engines also, they can essentially stay underwater more than a year. They don't have to come up. They have oxygen replenishing things. The only thing they might run out of would be food. So they have to have enough food to stay underneath if you want them to stay underneath. So as of right now, in times of peace, they're going to stay under for a while, maybe several months, come up, replenish the food, replenish everything, and maybe even change the crew out, and then go out and try not to be found. And that's kind of their job. That's a different kind of a job, isn't it? So it takes a very special person to even become a submarine a sailor. All right, what do you think about submarines then? Do you know that submarines could go down 100 meters and stay right there? Could they become neutrally buoyant there? Well, if they're sitting there at 100 meters under the water, which one's greater then, buoyant force or weight? They have to be equal again, right? Okay. I want to show you that. That was kind of a leftover, and I have another leftover. I thought I'd show you, and I know what you call this when you were a kid. Remember seeing that? Okay. Now, if you live there in Gaffney, South Carolina, you would not like people calling that the button in the air, but that's not really a butt. What is that? That's a peach, isn't it? Isn't that right? And they just wanted to have their water tower look like a peach, and so one side looks like a peach, but everybody else, that doesn't look good. All right. So I want to show you one other thing about that, and we know there's water towers all over the place. I live pretty close to a water tower, and what's that all about, you know? If you live not in the city limits, and you might live somewhere, and you would have what they call well water. Now, well water means that you have a pump, and you have somebody came one day, and who knows, they go down 150 feet, 200 feet. They drilled a pipe way down in the ground until you hit the main water source down there, underground water. Then when you need water, you turn on your faucet, and the pump pumps water out of the well, and it puts it somewhere, and so you have a supply of water. But if you have an electrical storm and you lose electricity, any of you in this situation, any of you not live in the city limits and you've lost electricity, does that happen? And so what happens? What do your parents tell you not to do? Don't flush the toilet. Okay, now, if you flush the toilet, you can flush that toilet once, but you're not getting any more water. So if you flush the toilet, you won't be able to flush it again. Now, if you live in the city though, do you ever notice that when the power goes out, you can still turn the water on? How's that? And if you think about it, during the nice days, water all the time is pumped up here on these water towers, and the water towers are up high, aren't they? A lot of times if you build them on a higher part of the city, you get even more water pressure, don't you? And so this water, the weight of that water is actually producing a huge amount of pressure, and that's going to all of your homes. Yes?
So, why would they not use the pumps instead of pumping it up, just pumping the water around?
They could. Even if the electricity goes out, if we lose all electricity, we still have a certain amount of water that you can have. So they could. I think they could. If you lose electricity, though, you have no water. This way, we do have water. So, and there are I don't know how many, couple million gallons. Some of these water tanks are a couple million gallons of water. And there are some people who study this. They say how much water people in Greensboro use every day, and they have several water towers and stuff like that. I agree with you. You could do that. This right here, though, if I pump it up here, I also have all this gravity. I have a huge amount of water pressure just because of gravity. And I can, like I said, if you have no electricity, you can still get it. I'm going to show you one more picture, and then I'll move on to today's lesson. Have you ever been in a big city? And if you've been in a big city, this is like probably a helicopter took this picture. Nowadays, you might get a drone to take a picture like this. But does anybody know what's on top of almost every big building in New York City? If you can't see it from the air, it's in the inside somewhere, but it's in the top. A water tower. You see, we have a problem with big buildings. If they catch on fire or something like that, how are they going to put them out? You say, well, the fire department. Well, yeah, the fire department, this building, yeah, they can reach up there. They have hoses that can reach up 3 stories, 4 stories. How about 10 stories? How about 20 stories? What are you going to do there? So one thing they have to do, as far as that, they can use that for fire protection. And it also helps them with water. It's hard to pump water up a 20-story building. So we have to have some storage there. I heard we had 2 different years, had Chinese exchange students, and they told me they very well knew that some of their big cities, they actually have rockets. They want to send rockets up there with water on them. So they're saying to fight, if you want to fight a big fire, they would try to send a rocket up there and deliver water. That's a different approach, isn't it? So anyway, I thought I'd let you see that. All right. Whoops. Ooh. All right, so now what I'm going to do is, the last thing I'm going to do is talk about this guy. The last thing we did on Thursday was get wet. And you remember the little device that had the little holes in it? And what was that guy's name? His first name is Blaise. What's his name? Pascal. So the last thing in this chapter has to do with Pascal's principle. And I'll read it to you and see if it makes sense to you. Pressure is transmitted undiminished in an enclosed static fluid. Okay, so what they're saying is, because you can't really compress liquids, if you try to compress the liquid, what will happen is any pressure you exert on that enclosed liquid, excuse me, it'll be transmitted to every surface. You say, what are you talking about? Like when I had that Cartesian diver, you're back here now. When I had that Cartesian diver, this is Cartesian diver number 1. And I need to have that air bubble. I need that air bubble to be compressed, because you can compress air. So how can I compress the air bubble when I can't touch it? And so this is an enclosed fluid, and if I put pressure on here, then the pressure I exert right there, it's exerted there and there and there and there and there and even there. And you can watch that little air bubble get smaller. Now when the air bubble gets smaller, that would create a vacuum, wouldn't it? So what happens to the vacuum? If the air bubble gets smaller, you'll create a vacuum. But there's an opening down here, isn't there? So what happens? What do you think? We did this last week. Brian, what do you think? You're right. So more water goes in there, right? And that makes the overall weight of the submarine heavier. Watch. The submarine now is more dense than water. Now, if I let go of the pressure, that air bubble will come out and expand and push some water out, won't it? I mean, this is called Cartesian diversion. But Pascal's principle said, I can actually affect that air bubble without actually touching it, can I? Now, you might think, wow, why is Pascal so famous? So somebody can squeeze a bottle and make an eyedropper go up and down? Is that why his name is in all physics books? Well, let's take a look. This right here, I can offer this as extra credit. I've done this in the past. It created some of the funniest videos I've ever seen. And you don't have to do this. As a matter of fact, I would not allow you to do it unless your parents gave you permission to do it. But what you could do is, imagine I took a glass cider bottle, something like that, okay? And I filled it completely with water. And then you go to the hardware store and find a cork that fits that opening perfectly. So I've overflowed the jug. I got my safety goggles on, and I probably have a tub underneath here. And I have this, I have my finger in the thing. And then what I'm going to hit it. I want to hit that with a rubber mallet. I'd use a rubber mallet because if you miss, you won't break the thing, right? So you have your finger in here, and you're going to hit this cork, and there's no air in it. Okay, got all the air out. You're going to hit this rubber stopper with this rubber mallet, like that. So what's going to happen? What's going to happen there? So let's think about this. If I apply a force, onto this amount of area right here, won't that create a pressure right here? Because pressure is force per area. Well, let's say the area is 5 square centimeters, and let's say the force is 10 newtons. How much pressure would I create? Pressure is force per area. So I would create a pressure of 2 newtons per centimeter. Has everybody got that? Now, where is that at? Here, here, in the middle, here, everywhere. Every single surface will have 2 newtons of force per square centimeter. Everybody get that? Now, what if I told you that the bottom of that thing had an area of 500 square centimeters? 500 square centimeters, and every one of those square centimeters had what? 2 newtons of force? 2 newtons times 500 is what? 1,000. There would be 1,000 newtons of force pushing on the bottom of that that container. Now, you might think, well, if the pressure is the same everywhere, it's just as likely that the glass will blow out the side as it would the bottom. But what's supposed to happen, except with some of the students who I've seen in the past, like I said, some of the funniest ones I've seen have been done by some students, but they're supposed to blow out the bottom before they blow out the sides. Anybody know why? Why would the bottom blow out when the pressure is the same everywhere? Why would the bottom tend to blow out before anywhere else? Let's see if you, on a Monday morning, whether you can think about something. Kinley, you think you have an idea? You're right. You are exactly right, because these all have the same pressure on them, but what else does the bottom have besides the pressure from my hitting this cork? It has the weight. Look how much water is sitting on top of that. See that? So it has the weight of the water and the pressure, and so in theory, the bottom should blow out, and that's why you have goggles on, and you have it in a tub, you got your finger on here, and a rubber mallet, and you hit it really hard, and not always, but most of the time, the bottom will blow out. The ones I've seen the most successful were the big gallon cider jars. I had a person that worked at Fresh Market. I don't know if Fresh Market now, because of COVID, they may not do that, but you used to be able to go in there and actually give you little samples of cider. You know, they wanted you to buy the cider. And so he had a bunch of them. He had a bunch of bottles. Fresh Market emptied them when they gave out the samples. So if you don't think you have one of these at home, you could ask around and say, do you happen to have any, cider bottles that I could have if you're thinking about doing that. Now, let me ask this question. Is Pascal famous because you can push on a bottle and make an eyedropper go down? Or you can hit a bottle with a rubber mallet and make the bottom blow out? Is that why Pascal's so important? Is that how he changed the world? No, he did. This changed the world. But the thing I'm going to show you here is a neat little device, and this is in the 1600s. The 1600s is when Pascal discovered this principle. And here we have a fluid. Everybody see this fluid? Hey, can everybody stop for a minute? I think you're doing homework, and I think what's going to happen is when you take the test tomorrow, you'll say, well, I didn't know that. And so my own opinion is stop doing homework for a minute and then pay attention, and then you'll have homework. You'll have time to do that kind of stuff. I don't know who that's for. All right. So now what we have is this situation where if I had this fluid and I had a piston over here and a piston over here, what if the what if the area of those pistons were the same? Then I could push down and the thing would go up, wouldn't it? It'd be like a teeter-totter, wouldn't it? Any pressure I create over here would be the same pressure here. And the distances would be the same, wouldn't they? Well, you can't do a whole lot with that. You can do a little bit with that. But what if you do this? What if the area over here is much smaller than the area over here? And this is what changed the world, okay? Now, I want you to think about this. Try to do some of the math with me, all right? What is the force over here? What is F1? Let's take a look at it. What's F1? And it says F1 is about 10 newtons. What is A1? A1 is the area, and it's about 5 square centimeters. So what is the pressure that I'm going to create on this piston? You say, what's force per area? It's going to be about what? 2 what? 2 newtons per square centimeter. Now remember, if it was newtons per square meter, it'd be called a Pascal, but this is a smaller unit. All right, now, the question now is, what is the pressure here, and right here, and right here? What's the pressure everywhere else? It has to be what? 2 newtons per square centimeter. But now, I don't think you see what's going on here. You don't see what's going on here. Say, big deal. Big deal. 2 newtons per square centimeter, and 2, and 2, and 2, and 2, and 2. So what? Big deal. All right, here's the big deal, okay? Because you guys are very mathematical, you should enjoy this. It's so mathematical. Watch what happens here. Tell me, how does the area of this compare to the area of that? A1 is 5 square centimeters, and A2 is 1,000. Get in the world of ratios and tell me how many times more area does the second piston have than the first? What do you think? Who feels like they can answer a question? Ella, what do you think? How many times greater is the area on this piston than that one? This piston's 1,000. That piston's 5. What do you think? 1,000 divided by 5. 1,000 divided by 10 is 100. So 1,000 divided by 5 would be twice that size. What would that be? So, this is important, okay? The area of this piston is 200 times greater. Now, because we're in the world of ratios, some of you might get mixed up a little bit here. It's 2 newtons per square centimeter right there. But look how many square centimeters you have here. You have a lot, don't you? You have 200 times the area. And every one of those square centimeters is going to have 2 newtons of force on it. So what's the total amount of force that could lift an object over here? What is F2? And this is where the world got changed. I put in 10 newtons of force. How much force comes out? It's very mathematical. And for those of you who like pure math, simply plug this into your second equation. Ready? 2 newtons per square centimeter has to equal the second force times the second distance. For those of you who just like to plug and chug, what is solve for x? Okay, what is F2? What is F2? Come on, help me out. Monday morning. Dave, what do you got?
What was the question?
If the pressure is the same everywhere, let's find out. I'm going to put that pressure into the equation. Pressure equals force times distance. Pressure equals force per area, right? So here's my pressure, right? And F2 and A2. This is A2. So if you had to solve for this, what I'm asking for is how much force is created on this second piston. And it's going to be 2,000 newtons. Is that right? Now, if you like pure plug and chug, you can put it in the equation. You'll get 2,000 newtons. But here's what I want you to do conceptually. Watch this. Compare the area of this to the area of that. How many times greater? And Ella said what? How many times greater was it? Remember? 200? Guess what this machine will do? This machine will multiply your force by 200 times. If you couldn't lift this object by yourself, what if I told you whatever force you put into it, I'm going to multiply it by 200 times? Or I could make another hydraulic system. What if I told you I could make it 2 million times? What if I multiply your force times 2 million times? Do you think you might be able to do some things with that? You think you might be able to move some earth with that, like backhoes? You think you might be able to lift heavy objects with a lever, with a single finger? And that's what hydraulics is all about. When I get in my car, I put my foot on the brake pedal. And what it does, it pushes on that fluid. It pushes on that brake fluid. And the brake fluid has a little tiny area, that little area, and it goes into a master cylinder, which has an area maybe like that. But guess what the area is on my brake shoes? It's like about that. And I have 4 of them. And so when I push on that, it gets multiplied. Whatever force I have gets multiplied many, many times, maybe 50 times. And that's enough to make the brake shoes stop my car. And that's called hydraulics. Now, because you guys are a little bit higher in math than everybody else in 11th grade, you should appreciate this. Yes, you can plug and chug and get the answer, but you can also think conceptually and say, doesn't this seem like magic, though? You're going to set this up, and you're going to multiply my force by 200 times? What? How did I get that? How did I get so lucky? It's not magic. You do pay a price. What price are you going to pay for having a machine multiply your force by 200 times? Ian?
The distance the other side travels up.
Say it again.
The distance the other side travels up.
Right. The distance you put in, the distance you had to push this plunger compared to the distance this plunger goes up, which one's going to be greater? D1 or D2? Right. If you're going to multiply my force by 200 times, I've got to put in 200 times the distance. Now, what was my D1? Look for D1 here. Whoops, where is it? Here it is. What if D1, what if I push this plunger down 100 centimeters? Now, how much will the other piston go up? 1/200th. What's 1/200th of that? Half a centimeter. Now again, even though you think, I don't know about this, that trade-off like that, it's a great trade-off. If I've seen people lift an engine out of a car, one person, there's no way you can grab the engine and lift it up there. But they set up a tripod with a pulley system and has a chain on it. They hook the chain on the engine. And they just go like this. They don't even sweat very much. And they pull out a couple 100 feet. It's the same chain, just going in a circle. 100 feet of chain comes out, and here comes the engine. Here comes the engine. Here comes the engine. Here comes the engine. Now, they're willing to put in that extra distance to multiply their force. You get it? Would we want to break something? I mean, break something that's almost unbreakable. We can set up a hydraulic press. Multiply your force by 2,000, 3,000 times. You could do that. Yes?
So when you make something like a hydraulic press, and there's a bunch of force going in that one direction to crush something, isn't there also a bunch of force on the actual machine itself? Like, so how do you, if you want to press something with like an insane amount of force, how do you keep the sides from blowing up?
Okay, so what I could do is, if I have a hydraulic system, and here's my main cylinder, okay, here's my main cylinder. What if I have the main cylinder hooked up to 20 other cylinders, and they all have bigger areas? Then each one of my 20 little things I wouldn't probably blow the side. You're right, I have to build it strong. I agree with that. But the pressure is the same. As far as the pressure, it's the same. But if I could make one of these and split it up into many, many little fingers, I could multiply my force by thousands of times. You're right. If I only have one cylinder, I got to make it pretty strong because the forces that are there are going to be great. Yes.
What was the equation you used to calculate how far it would
Okay. If you have a machine that multiplies your force 200 times greater, right? You got to put in 200 times more distance. Now, it said down here that the distance that I put in here is 100 centimeters. So that's 200 times bigger than what number? What's 1/200th of this? And that comes out to be 0.5 centimeters, like that. The one the handout sheet that's in your packet, did you guys get the practice test packet? Remember the practice test packet? Okay. The one that's in there, a student made up those numbers, and they're kind of weird. I think he made it so that it multiplies your force by 130 times. I think that I just use kind of simple numbers. But did everybody do that yet? You don't have to do that. It's a practice test. If you want to sit with somebody tonight, or you might want to use that. Yes?
So, for like the car lift examples, do they have to push it down, like make your distance a lot greater to lift it up?
Right. Now, what's happening here, I'll show you the picture in your book. This is one of the things you had to draw for homework. I'll show you a picture here. Here it is. Now, the one that's in the book shows a 1 Newton force, and what's the area here? Is it 1? Yeah, 1 square centimeter. And look over here. How many square centimeters is that? 50. So the area is 50 times greater than that, right? So what's it going to do to my force? What's it going to do to my little 1 Newton force? Keep looking at your faces. Marie, what do you think? The area over here is 50 times greater than this area. So what's going to do to my 1 Newton force? By what? Yes. What's 50 times 1? So guess what? With a 1 Newton force, I could lift a 50 Newton object. Now, I also will put, what if I put in 100 centimeters of distance here? I have to put in 50 times more distance than you move. What's 1/50th of that? Everybody? 2. So this will go down 100, this will only go up 2, but guess what? I lifted it, didn't I? I lifted it. Some of you know about levers. Here's this big rock. I would just want to move that rock. I just want to get a rope underneath that rock, but I can't lift the rock up. So you put a lever in the ground, don't you? And you go like this. And your hand moves this far, and the rock goes up this far. So that's okay, because that's all you really want to do. You just want to lift it up high and get a rope underneath it, didn't you? But I did it. Some people have windows that get stuck. You ever done that? How do you get a window that's stuck? You ever use a crowbar? Okay. Now, I think I'm going to answer your question with the next one, right? So what happens when I go and they put my car up on a lift, and is that what they do? Does the person who runs it, do they run around the block pushing a piston you know, 200 feet, so the car will go up about 5 feet? Is that what they do? No, somebody figured out a long time ago, here's my hydraulics right here. Okay, here's my piston, here's another one. Instead of me pushing something a really, really big distance, I simply put some air in here, hook it onto a compressor, flip the switch, and the air, like little fingers, push, 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 push. See that? I'll let the air do the pushing for me. And I'll just let the air lift that car up there, up on the lift, like that. Is that what your question was? Yeah.
But do you have to have like that same amount of? Do you have to have a greater amount of distance of air that's pressed and then?
It all depends on how you set it up. If you set it up so that they call it the output force. If you make this area bigger than that, it'll multiply your force. What would be a reason why somebody might want to use this as input? I'm willing to put in 50 newtons of force and only get 1 out. Why would you want to do that? That's dumb. What do you think?
A weapon?
It could. So if I put something here, if I were to move this down 2 centimeters in 1 second, this would move what? It would move 100 centimeters in 2 seconds. It would multiply my speed by 50 times, wouldn't it? So most of the time, that's not what we're doing. But most of the time, this area is bigger than this area. And as long as this is bigger than that, it'll multiply your force, but you have to put in more distance. What if they were even like this one? What, 10 newtons, 10 newtons. Down 5 centimeters, up 5 centimeters. See that? I could make one that's even, like that. But what changed the world was being able to multiply your force. You know, jet airplanes, when you're going at 800 miles per hour, and you want to make the flaps go down, or you want to make a turn, that's just not easy to do, is it? Can you imagine being out there 800 miles per hour, and you're trying to make a piece of metal go down there against all that wind? How do you do that? I need hydraulics. Yes? Hey, I got a dump truck, and I need to dump, 3 tons of dirt. How do you go do that? Hydraulics. Yes?
Do they use water in hydraulics or another liquid?
Yeah. Now, water's okay, except if there's any little tiny leak, it can evaporate. And so they do use water. They can use water for sure. Hydraulic pumps and things like that. But most of them, they have hydraulic fluid, which is more of an oily-like material. Less likely to evaporate like that. Great question. Yes?
Wouldn't water not work if it was in a cold environment because they could freeze?
That'd be another reason not to use water. But if I had a source of water and I could set one of these up and I didn't have, I could see using water if I had to, but I wouldn't use it in a place where it freezes. You're right. Do you know there are places that even the hydraulic fluid, if you're not careful, it can freeze. Actually, it's really, really cold. So they have to be careful about that too. All right. Well, we're pretty much finished with everything. What I was wondering about, any questions you might have had? Yes?
How cold would it have to be for brake fluid to freeze in the car?
Wow, you know what? If you look that up, I'll give you credit for it. Look up brake fluid and look up freezing temperatures and brake fluid. I don't know the answer to that. I do know that if I lived up in northern Canada or in Alaska, I'd probably have, it's very possible that the brake fluid might be a little different, maybe. But on the other hand, maybe not, because what if I drive from North Carolina to Alaska? I wouldn't want my car to stop working. But that's a good question you had. I don't know the answer. I bet it had to be really cold, like that. All right, what about, as far as the homework and everything, what kind of things you still had trouble with? How about, did you understand question 29? I'm just looking at some of those. It says here, a sketch shows a reservoir that supplies water to a farm. It's made of wood, reinforced with metal hoops. Why is it elevated? I'm sorry. My fault. Why is it elevated? Even on farms, they have little water towers. You know that? Why is it elevated? Help me out. Yes.
So that you can create greater pressure.
And how do you do that? How do you create greater pressure?
Well, the more deep something is.
You're right. It's the depth. You're right. I have a pipe connected to the water tower, and the depth is very great, isn't it? Why are there more hoops down here than up here? Yes.
There's a greater pressure of water in there
Why?
because of the depth.
Does this make sense? Okay. How about 43, question 43? There's a hydraulics question. In hydraulic arrangement shown, the larger piston has an area 50 times that of the smaller. The strong man hopes to exert enough force on the large piston to raise the 10 kilogram. Now he's doing a reverse, isn't he? Is that right? So what's going to happen here? He wants to raise the 10 kilogram mass, which is 100 newtons, right? So what do you think here? Do you think he will be successful? Did anybody do that question yet? Now he's using a hydraulic system kind of in reverse, isn't he? So what he's going to do is he doesn't want to have to push it very far, and this will be pushed a great distance, right? But if the area is 50 times greater here, he doesn't get a multiplier force by 50. It'll actually diminish his force by 50 times, won't he? So what's going to happen if how much is he pushing by? Oh, he has to come up with 100 newtons, right? Now, so how much is he going to have to come up with? He's using it in reverse. If I did it the other way around, 100 newtons would equal 50 times 100 newtons. It could lift that high, right? So same thing. He wants to lift a 100 newton object. He's going to have to come up with how much? 50 times 100, which would be 5,000 newtons. Now, can he come up with 5,000 newtons? That's a lot. And let me see what the author said on this one. The author says, no, scale measurements, blah, blah, blah. That's a terrible answer. Okay. 45, sorry. Unsuccessful to push with 50 times the weight. He would have to come up with 5,000 newtons, which is more than he weighs. Anyway, so he's using a piston system in reverse, and I guess he was trying to get distance out of it like that.
He could weigh 500 newtons.
He what now?
It may just not be good.
It's actually 5,000 newtons, I guess, is more than he even weighs. So even if he sat on it, he wouldn't be able to come up with 5,000 newtons.
What I'm saying is maybe it doesn't depict him perfectly. Maybe he's actually 500 newtons and he's just really fat.
500 newtons, though, wouldn't create enough pressure or force per area to lift that thing at all.
I mean 5,000.
Oh, 5,000?
500 kilograms.
Oh, okay. 500 kilograms would do it, but that's a lot. 500 kilograms times 2.2 pounds, that's like over 1,000 pounds. I mean, that's a lot, isn't it? Yeah, so I don't think he weighs 1,000 pounds. All right. I have one more hard question for you. I have a hard question for you. I've had people do this. They just couldn't believe it, so they did extra credit, but you don't have to. You take a glass and you don't fill it, you put water to a certain level, and you take a marker and you mark on the glass. See that? And then you put in like 3 ice cubes. And the water level goes up, so you put another mark on the glass. See that? Everybody got that? Now, ice cubes are floating, aren't they? So not all of it is underwater. But they're floating, aren't they? What is the weight of the water that's displaced by the floating ice cubes? What is the weight of the water of the floating ice cubes? It equals the weight of the water displaced, doesn't it? So the question is, you put your first mark, no ice cubes. You put the 3 cubes in there, put a second mark. The next question is, let the ice cubes melt. What will happen to the level of the water? And some people don't believe this, that's why they go home and do it. Ready? Water with no ice, water with ice. Wait a couple hours and mark where the water level is with the melted ice. What do you think? What do you think? Down. How many people say down because Marie said it? No. How many people say down because it made sense what Marie said? How many people say the water level will actually go up? Because not all the ice cube is underwater, and after it melts, up. Okay, I got an up vote. How many people say the same? I know you don't gonna like this. The level's gonna stay the same. Because one more time, when they're floating, they still displaced the total weight of the ice cube. Even though the whole ice cube wasn't underwater, it displaced the total weight of the ice cube, didn't it? So whether the ice cube's melted or not, the total weight has been displaced already. And so, anyway, when this thing melts, it's going to stay at that second level right there. So there are several questions here that are a little bit more difficult, and they really take some thinking. Some of these, here's one of my favorite. Do I have 2 more minutes? Is that right? Here's one of my favorite questions here. A gravel barge, rectangular in shape, is 4 meters wide and 10 meters long. When loaded, it sinks 2 meters in the water. Show that the weight of the gravel is 800,000 newtons. What? How are you supposed to do that? Well, first of all, what is the volume of ship that is underwater? What's the volume of the ship that's underwater? When loaded, it sinks what? 2 meters in the water. Okay, so what is the dimensions of the part of the ship that's underwater? It's 2 meters by what? By 4 by 10. 80, is that right? How much the boat is underwater? 80 cubic meters. Is that right? Okay. Now 80 cubic meters of water is how much? Does anybody happen to remember that? Here's a cubic meter, right? How many liter boxes? How many liter boxes fit in a cubic meter? How many liter boxes fit in a cubic meter? I'll give you a clue. 10 go this way, and 10 go that way. There's 100 on the bottom floor. 10,000. A cubic meter, a cubic meter is 1,000 liters. You get that? So how much does that weigh? What mass, I mean? Per times 1,000. 1,000 kilograms, right? 1,000 kilograms is how many newtons? Uh-oh. 1,000 kilograms, how many newtons? 10,000, isn't it? Does you multiply by 10? All right, look right here then. If 80 cubic meters is underwater, then 80 times 1,000 is this many, 800,000 newtons. 800,000 newtons, and they said, prove that the gravel weighed 800,000 newtons. We did, because the weight of the water displaced is 800,000 newtons, like that. Okay. I will be here today after school, and I'm not meeting anybody except physics people. So if you're here after school today, I would like to be here to help you study. And we'll go right from the beginning. We'll start at the beginning, go all the way through the chapter, and you can ask whatever question you want. And so we'll be here after school, probably start around 3:20 or 3:25. Okay? All right, well, thank you.